Hello everyone and welcome to this tutorial where we're going to start getting to the basics of electronics. Now for this first video what we're going to do, we're going to try and have a basic understanding of electricity and how electricity works and the basic components of electricity. Now I'm going to start off with a little bit of history, a little bit of science, and also just give you a few basic analogies to understand the different types of electricity, i.e. AC and DC. So I'm going to talk through these just to start planting a few seeds in your head before we get down to some of the theory. We're going to do a very basic theory on some paperwork and with some practical examples as well to show you a few bits and pieces. Now, I don't want you to get too caught up obviously on the history. It's there for interest, and the science side of it, again, it's just good to have a little bit of background, but basically we'll get down to the fundamentals when we start looking at the bits of paper. Basically, electricity was discovered a long time ago. Now, it was discovered apparently many years BC, in fact, in the form people started seeing electricity in the form of static electricity, or in fact even they started realizing with things like certain catfish and what have you, when they touched them they got a shock through their bodies. So that's when the notion of electricity apparently started coming about. Static electricity, obviously, when certain objects were charged and reacted, that kind of led to a discovery on electricity and static electricity and what have you. The first real work on electricity and calculations and theorizing came around in the 16 and 1700s. And kind of the more practical applications of electricity started happening in the 1800s. So as an example, let's say the practical like electrification of houses because of the invention of the incandescent light bulb came around the 1880s. In fact, in 1881, apparently, and this was news to me because I thought it was America first, but believe it or not, in Surrey in the UK, believe it or not, that's where I was born, there was the first central power station which provided electricity to a little village. A little village had a vote because at that point in time they were running on gas power. The gas power wasn't economical, so they decided to implement this new thing called electricity. They did implement that first power station, but apparently it wasn't very economical, so they actually reverted back to gas. But the kind of main power station to come online and start feeding street lights and houses happened in the States, in New York. That was in 1882, so a year later, and that was the Edison's Pearl Street station. And they started off with using DC, so direct current, and they only later switched to AC. Now, so let's just talk a little bit about AC and DC. Now, basically, once we get down onto the piece of paper, I'll start explaining this, but DC, direct current, is electricity just flowing in one direction constantly, while AC is basically electricity in a conductor going backwards and forwards, pushing backwards and forwards, almost like a piston on a steam engine, backwards and forwards. And because of that reason, there's far less effort involved pushing something backwards and forwards than constantly trying to push it in one direction. Another analogy to give you an understanding of AC versus DC, if you picture someone sawing a log, you've got a saw and you're pushing it back and forth. You push it, you've got to pause, you pull it back, you've got to pause, you push it, you've got to pause. So there is this pause, and that is a creation of a sinusoidal wave where electricity goes up to a certain value, comes down to the 0 point, and then goes negative and then comes back again. And I'm going to demonstrate this on a little oscilloscope as well. We'll look at the mains electricity. Whereas if you can picture that same person now having a circular saw with a handle that they're having to crank around at a constant pace, your arm's going to get a lot more tired doing that than that saw that's going back and forth where you've got to pause. But if you picture the saw blade on the log, whether you're cranking a handle round on that circular saw, or you've got that saw blade coming back and forth, it's still having the same result on the wood. It's doing the same bit of work and cutting through the wood. Whether you're using AC or DC to constantly cut on there. So I just want to plant those seeds in your head at the moment. Now to get down to the science. And again, I certainly don't want to get bogged down into too much scientific stuff or even formulas at this point in time. That's going to come in due course when we start get down to working with components and putting circuits together. But in essence, electricity is a flow of electrons through a conductor. Now we're going to be using fluid dynamics or fluid mechanics to explain this, because it is fluid mechanics and dynamics have got a very good correlation to the way electricity works. But in a conductor, a metallic conductor or something that can conduct electricity, you've got atoms and electrons in there, and basically it is the flow of electrons from negative to positive that provide a current potential or electricity. Now, so that is the converse of what we generally work in, where conventional electricity we say flows from positive to negative. So I don't want you to get confused, I just want you to understand the science behind it. In fact, that electrons flow from negative to positive, that's the science side of it. But for all intents and purposes, what people use day to day and what we'll be using in our explanations is conventional electricity flow, which is from positive to negative. In terms of direct current, obviously as you will see with alternating current, it's a change. It's actually going back and forth and cycling in two directions. Okay, so let's get stuck down, have a look at the piece of paper and see what I've got there. Okay, so let me explain this diagram that I have here then, and we'll start going through the individual components of it bit by bit to have an understanding of what it all means. So basically, this in essence is a big water pipe, this big round circle rectangle over here. This over here is a pump, a water pump. Over here we have a valve which can be closed or open to allow water through. Over here is a paddle, or basically in essence an appliance, and in this case it's a paddle driving a shaft into a mill, where let's pretend that basically we're milling or grinding flour or wheat into flour. Then we've got over here our gauges, our pressure gauge is telling us the pressure of the water in the pipe, as you might literally in a pipe system. And then over here there's a paddle which basically is measuring the flow of water in the pipe and displaying it. It's spinning around and it's displaying in essence like, if you like, on a rev counter on a meter over here. Right. So let's first of all start with our pump. Now over here you'll note if we relate this to an electrical circuit, the pump over here is in essence our power source. Now see here I've got power source in inverted commas because ultimately, again, if we talk about the science of electricity, you can't really create or destroy energy. So it's not a source per se, but it is the piece that actually generates the flow of energy in our circuit. So I'm going to call it the power source or the pump. In essence, it could be a battery or it could be your mains outlet in your house. But this is what, in essence, creates the pressure and the flow to get water flowing around this pipe system. And in essence, that pressure and flow ultimately is the electricity flowing around this circuit or this pipe system. Now on this pipe system, as I've said, we've got these pressure gauges over here. And these pressure gauges are measuring the pressure of the water. They don't have to be inside the pipe itself. You only need a small little tap into your pipe to actually pick up the pressure. Now the pressure of the system equates to your voltage. So when we refer to a voltage in a circuit, that in essence is the pressure which is there to push the water, or in essence to push the electricity through your circuit. Now, as you can understand, and this is something we're going to cover off probably in the next session, where if you've got obstacles inside your pipe, i.e. like a valve or an appliance or what have you, they are going to create a restriction to the flow of the water around your circuit. And that restriction in essence is the resistance. So you need enough pressure to overcome that resistance and those restrictions to allow you to have water flowing or electricity flowing through your circuit. Now let's come down to this device over here. So if we want to measure the flow of electricity through our system, or the water flow through our pipe system, we literally have to we can't just have a little simple tap into the pipe to read the pressure as you can in a water hose or what have you. You actually have to place something in a little paddle or a turbine or what have you inside the flow of the water to start measuring it. And it's likewise when we have a multimeter and you want to measure current, you need to place your multimeter in circuit to do this. And it's exactly the same with measuring water. You have this paddle in there and that spins around, and that then on a dial gives us the flow. Now flow of electricity equates to the current, which is amps. And so there's something quite important to understand. Let's pretend that I go and close this valve over here so that I have no flow of water. Do you understand that this pressure gauge over here is still going to show you pressure? The water's pushing against it. It's going to be pushing up into that gauge. You're still going to have pressure. That pressure, remember, is voltage. So you still have a voltage potential pushing hard against over here, that water pressure. When you start opening this valve, that starts allowing the water to flow. Then when you've got flow, you've got current. And current is amps. So flow through a circuit is current, which is amps. So now there's something important also to note about flow. When you start talking about flow rate, rate implies time. And as soon as you start adding time to the equation, flow rate, then you're talking about consumption or amp hours. And this is important because, again, what we're going to do, I'm going to have a practical demonstration now. Also, in some of the normal videos I'm going to be posting soon on batteries and battery testing. All these components relate to each other, and you'll have a good understanding of what I'm doing for that battery testing if you're following what's going on here. So the flow rate is basically your flow over time is an amp hour, and that is what equates to consumption, what you're using. If you had a little bucket catching your water at the end of this and that bucket is filling up, that filling of the bucket would equate to your consumption, how much electricity you're using or how much energy you're using. Also, so it's quite a nice analogy here with using the pipe, this closed pipe system with a pump and a valve and pressure gauges and something that's measuring the flow. It's like an electricity circuit. It needs to be complete. It needs to be intact. That intactness is something we would relate to something called continuity. And it's obviously continuity is something that you can use a multimeter to measure. Now, I'm talking about a multimeter. If you go and see my video series on how to use a multimeter for beginners, I then equate a lot of this and how you'd measure these bits and pieces with a multimeter. So if you are new to this, then those videos will help you as well. And I'll annotate with one of those here. Right, so that going back to that continuity, you need the pipe intact to allow your water to flow through the pipe system. Likewise, you need to allow electricity to flow. You need an intact system of conductors, i.e. your electrical wires. If you have a break in your electrical wire over here, just likewise if you broke the water pipe and the water would in essence start spilling out, and then your mill over here would stop working because you wouldn't have water flow. Now in reality, if you cut a wire, you're not going to see electrons flowing out the edge, hopefully. But the analogy is the same. If you break the pipe and the water's basically flowing and not going back up through the system, then you're not going to have the water flow to power your mill. Likewise with the wiring system, if you have a break in your wiring system, the electrons are going to stop flowing, your appliance is going to stop working. So let's now pretend we go back to having a complete working system. Let's go to the ultimate reason we have electricity, and that's ultimately to power a device and to do work. So here, as I said, we've got this paddle which is driving a shaft which is turning a milling stone here, which is milling our flour, let's pretend. So in essence, that equates to an appliance that you might have in your house. Now, basically, if you've got taking the energy out of the system to appliance, that is the work being done by your water or the work being done by your electricity, and that equates to power. So there is a close direct relationship between your pressure, your flow, and the work being done, and that is there's a direct relationship between voltage, current, and power. And we'll start looking at this in particularly when we start looking at resistors and Ohm's law, those relationships and how they interact. But from here, all I want you to understand basically is that the end result and what you're looking for in terms of electricity and the flow of electricity is the work being done, your appliance being connected to your wiring system, which in essence is using power, which is a combination of your voltage and your current. Likewise, although in essence in this system our pump, let's pretend our pump is pumping our water around in a single direction, that would equate to direct current. A single direction of your electricity flow, constant push through the pipe system. Now equally you could still get your work done, as I was explaining with a saw cutting the piece of wood. If this pump had a piston in it that was pushing backwards and forwards instead of pumping in one direction, as you can imagine, your pressure gauges would be dancing around, going back and forth. And that's exactly in essence what happens with alternating current. Your voltage is then fluctuating up and down, positive and negative. But even though you've got that flow of electricity going back and forth, as you can see, your paddle is still going to be flipped backwards and forwards. It's still going to grind your flour at the end of the day. So in electronics, and that's why we are going to focus after this mainly on direct current, because that's what we use for the most part in electronics. But understanding electricity, you can see that direct current can power things, and alternating current, which is used in your house, can power things even though it's going back and forth, in essence going on and off, because it still does work at the end of the day. Now let's quickly actually discuss why alternating current is used as opposed to direct current for your house. As I said, it takes a lot more energy to use direct current.
on a big system. Once you start getting to the higher voltages and what have you, your losses across a piece of wire become far greater with direct current, because the amount of energy required to push that constantly in one direction as opposed to back and forth. So that's the one reason. It takes a lot more energy and your losses are higher. You need far thicker wire to make it easy for the electricity to go through for direct current than you do alternating current. The other reason is, the reason AC is used is that you can generate far higher voltages with alternating current, and that's far easier to transmit higher voltage over long distances and then transform that down to a lower voltage and get the current back once you get to a neighborhood or your house. So you can transfer voltage, high voltage at low current, so you don't need thick wires, you've got less loss, and then you transform that back to your normal voltage when you get to your house.
Okay, so let's actually pull away from the paper quickly and have a quick chat about the mains electricity that comes into your house. The one thing obviously is that you'll realize AC, besides being more efficient to transmit over a longer distance, it's also safer because you've got that pause while it's going back and forth. Because it actually goes through zero and back again, it's safer than DC, because DC is constantly on, and if you touch or get electrocuted by electricity, AC, you've got potentially it's gonna kick you away, whereas DC will grab onto you because it's just constantly on and you tend to clench up and hold, whereas AC tends to throw you away. So DC will potentially impart far more energy into you as well than AC will, if you have comparable voltage and current. Now, the one interesting thing I discovered, and it's something to highlight, obviously, that around the world different countries use different voltages and frequencies. Now, the frequency is obviously, as I'll demonstrate, is you'll see that sinusoidal wave as the electricity is going on and off, and that happens at a certain rate. Now, here in South Africa we use 220 volts at 50 hertz, so 50 times a second the electricity is going through a cycle of on and off. In the States it's 110, and at a rate of, it's 110, 120, and it's at a rate of 60 hertz, so 60 times a second. And one of the big reasons for having the use of 110 or 120 in the States is that it's obviously far safer. You've got a lower voltage, and the combination of the voltage and the current, because the current supply is still roughly the same. To a normal household outlet, it's roughly 15 or 16 amps. Same in South Africa, same in the States. But now the one interesting thing to note is there are limitations with that safety factor in the States. And that is, particularly when it comes to tools which need more power. So the combination of your volts and your amps give you power, and you've got less of that in the States from a standard 110 outlet. And when we lived in the States for 2.5 years, I came to realize this, and I couldn't quite understand something until I then clicked about not having enough power. I really enjoy drinking a cup of tea. I'm an Englishman, even though I live in South Africa, I enjoy my cup of tea. And for that reason, when we got to the States and we had to buy our appliances, we went looking for a kettle. Now in the States, I couldn't understand in people's houses why everyone had kettles which they put on their stove, on a hob, on the top of a plate to heat the water. It just didn't make sense to me. A kettle makes far more sense. It's just easier to fill up, switch on, it switches off automatically, whereas a stove doesn't switch off automatically. But then I realized, generally speaking, kettles require a lot of energy, a lot of power to work. Often a kettle will be rated, will run at 2,300 or 3,000 watts. And in the States, if you look at how much power you can get out of your 110 outlet, often it's not enough to drive normal kettles which you'd find, let's say, in South Africa. So for that reason, I realized that's why people heat their water for their coffee, or not that people have coffee makers, but for tea, you'd have something on a stove. Anyway, I did eventually find a kettle, but I hunted high and low in the state to find a simple plug-in kettle. Anyway, let's get back to the analogies and the examples. I'm going to show you what AC looks like, and we're going to do a demonstration with DC to explain pressure or voltage between two sources. And this becomes important again when we get to the battery testing, because to charge a battery, you've got a battery with a certain voltage or a certain holding pressure in it as a vessel with pressure. To charge it, your charger needs to overcome that pressure. It's like if you've got a vessel with a pressure and you've got a pipe going into it and you want to push water into that vessel, you have to have a greater pressure pushing to get it inside there, or else it's just going to push back. Likewise, charging a battery, your charger has to be at a greater pressure or a greater voltage to charge your battery. Equate it to filling up a balloon with air. When you blow air into that balloon, you have to have a greater air pressure in your cheeks to get the air into the balloon. Likewise, pumping up a tire of a car or a bicycle, you're going to have a certain air pressure in that tire, and you have to have a greater pressure that you're pushing in that pump to get air into that tire. Let's go have a look at some practical examples. Right, so let's have a look at our mains electricity here in South Africa. I've got this Unity UT81B. If you are interested in it, there is a little review on it if you've not seen one before, and I'll annotate that here. Basically, it's a fairly useful device. It's a scope meter. It's a mix of a multimeter and an oscilloscope, so we can get to see wave electricity signals basically. Now what I've done here, these two probes, as you can see, I've got a multi-strip specially set up with a connecting block there where I take off the electricity. Or be very careful about working with mains electricity. I certainly don't advise you to go get your multimeter and just willy-nilly sticking the probes into outlet. Mains electricity can bite you, it can blow things, so please be careful. I'd rather hope that you're watching this example than trying to do this yourself, because if you do it wrong and touch things that you shouldn't, you can hurt and injure yourself. Right. As you can see, I've got this set to measure voltage. I've set it to measure AC voltage, and we've got a figure of around 230 volts. Now I'm going to change the mode of this, so we go into it's kind of scope mode. I'm going to push the auto button so that it sizes things up for us, and as you can see there, we've got this sinusoidal wave happening. So let me just change the period that we're seeing. So what we can see here is a sinusoidal wave which is going positive. We've got this, in essence, these crosshairs here, and this is the zero line. So this is the voltage going up, positive, and then coming back down, negative, up, positive, down, negative, and that's that back and forth motion in essence which is being measured. And as you can see here, we've got the voltage and we've got the frequency here in South Africa is at 50 Hertz. And on this meter, what you can do, so that's the frequency, and if you count we've got this set to 10 milliseconds per division,
And if you count the divisions where you've got a repeating cycle, so there a cycle starts, that's half of the cycle, and then that's the completed cycle over here. It's 2 divisions. That's 20 milliseconds. That's the period or the time it takes to complete a cycle, 20 milliseconds, and obviously you get 50 of those in a second. So that is what AC voltage looks like. Now I'm not going to concentrate too much more on AC voltage because obviously in electronics we predominantly use DC, but I'll show you what DC looks like on a scope. Right, so I've got my variable DC power supply set up in the background. It's preset at 13 volts. I've got a range, I can vary that. I've got it preset to a certain range of voltage because we're going to do a demonstration with a battery after this. I've got the Unity scope meter linked up. I've got it set to volts. At the moment it's set on AC, so I'm going to change it so it's back to DC. And then I'm going to now switch on the output of my power supply. And as you can see, we're measuring, it's showing us a reading of 13.1 volts. And obviously as I change the setting on the variable power supply, you can see the voltage or the pressure changing. Now let's go over to the scope. So as you can see, there's that line, a straight line appearing on the scope. Now let's try and get that so you can see with no reflection. And as I vary the voltage, you can see the voltage level being noted there. You can see that straight line just going, its height is changing relative to the 0 line, but it is dead straight. It is constantly on, constantly pushing. That is direct current. It's not going on and off as we saw with AC. And that's what a DC signal looks like on an oscilloscope. It is just straight on the whole time. Okay, so what have we got here now? Now we're moving over to our battery. This is a 12 volt lead acid battery. I've got it connected up, the positive obviously onto the positive and the negative onto the negative. That's the polarity. Now I've also got my variable power supply sat here, and I've got this WhatsUp meter. Now the WhatsUp meter currently is actually showing you the voltage or the pressure, the voltage potential that is sitting inside the battery. It's sitting at about 12.998 volts at the moment. And as you can see, here is the meter that also shows you where there's a flow of electricity measured in amps, and that is at 0 at the moment. So what I'm going to do, I'm going to turn my power supply to roughly match the voltage or the pressure that's sitting in the battery. I don't know if I'll get it exactly right. I'm going to switch it on now, and I've kind of got it spot on right, because if you look here, the dial over here or the digits over here show that basically there is no flow of electricity, and likewise there's nothing going into the battery because the pressures are the same. Right, so watch what happens as I start to step up the voltage and the pressure. As you can see, we start to get a flow of electricity, which is being measured in amps. In this case, it's milliamps. So it's only small. You can see there's the power supply showing, and the meter, the WhatsUp meter over here is showing that there's a flow. So because now my voltage or my pressure at this point is higher than the battery, I can actually start pushing back energy or electricity into the battery. And as I obviously step up that pressure, I increase the pressure, I increase the voltage, likewise then the flow starts increasing and I get more flow into the battery. As I said, just think about the blowing up of the balloon or the pumping up of the tire. Then if I drop the voltage, actually let's just go take it up more so we can actually get a real representation. I've now got a kind of the highest, safest pressure that I'd want to push back into this battery. And again, an analogy here is that if you're blowing up that balloon, you think of the walls of the balloon are not that thick. If you had to have a very high air pressure pumping air into that balloon, potentially you're going to rip and shred these walls of the balloon and burst it. And likewise, it's the same with electricity. If you do things too quickly, have too high a voltage or what have you, you can damage appliances. So here, as a safe voltage or pressure at 14.4 volts, I've set it up and we're pushing, we've got a flow of electricity at 276 milliamp going into the battery. And slowly but surely that will build up because we've got, in essence, a closed vessel here, in essence, with the battery. So it's, as we're pushing more energy and more pressure into it, its pressure is going to build up, i.e. its voltage is going to build up. And that will give us an indication of the level of energy storage and charge inside the battery. Now I'm going to do the other. I'm going to drop the pressure or the voltage on my power supply and just note what happens. Obviously we've got a slightly high, we've pushed up the pressure in the battery. I'm still got a slightly higher pressure on the power supply at the moment, but look what happens as I drop below what the battery is. I've got a negative reading on my power supply. So in effect now what the battery is doing, because the battery's got a higher pressure or higher voltage than my power supply, it is trying to push electricity back into the power supply. Now basically you can't really push power back into the power supply. It's not designed for that, but in essence, as you can see, it is doing it to a certain extent. And all I want to show is there is pressure differentials or voltage differentials determine the flow, where, how electricity is going to flow. That'll be important certainly once we start getting to looking at electronic circuits with different power sources and what have you. Okay, and let's just look at that in terms of this diagram again, in terms of different voltage potentials or different pressures in a system. If I had to pretend that this valve over here was also a pump, but it was pumping in the opposite direction to this pump, you can understand that whichever pump was pumping had the highest pumping pressure, they would be the one that would be winning the kind of direction in which the water would be flowing. Likewise, if you had a second pump here flowing, pushing in the same direction, you then get another scenario where you're going to get more higher pressure through the system. And once we get down to looking at circuits with parallel and series power sources and resistors or what have you, we'll come back to that analogy to start explaining exactly how that all hangs together. But just the important thing to walk away with from this session is correlating is that fluid dynamics and pipes are a very good way to understand how electricity flows in wires, and to understand that pressure equates to voltage, that your flow is your current or your amps, and that obviously those closely relate to the actual energy you're imparting to your appliance or whatever you're trying to power.
Okay, so I hope you gained some value out of that first in the series. Thanks very much for watching. Again, what I ask you to do is certainly if you've picked up any mistakes or errors in that, do post comments down below and I'll either annotate or correct them with a follow-up video or what have you. I'll also have a link to this video in my forum so that we can build up a series on the forum where it's far easier to have open discussion. It's far easier to see input from other people who are certainly perhaps wiser than I am and can add some good value to this series. If you would like to support this work that I'm doing, then certainly what you can do on my website, and you can either make a donation, you can be active in the forum. I have an Amazon store that you can purchase things from, or literally just rating the videos and watching them supports what I do. So I do appreciate your participation and literally just watching the videos. We will continue this series. I plan to literally, as long as there is support for them, we'll continue. The next thing we'll look at is obviously resistors. We'll start looking at the components like resistors, Ohm's law, diodes, transistors, logic gates, and even things like the 555 timer, and then start putting circuits together and what have you. So as I say, if you are gaining any value out of this, then certainly do subscribe and follow this series, and I certainly hope you learn something from it. Thanks very much for watching, and I'll catch you soon for the next one in the series.